Yeah, good evening. Welcome to the session on previous year questions for ISRO. I wish you all the best for the young aspirants those are going for the exam prior. And I am Dr. G.S. Sharma representing ACE Engineering Academy. And then today I am trying to discuss about conduction, convection, radiation and heat exchangers. The questions that were being populated from last 5 to 10 years, the different questions that have been more typical in the sense what are the repeated questions and how they are trying to give from where particular concepts they are trying to give it. So if you look at the questions, they are stretched up into conduction, again a subtopic in terms of convection, then radiation, then heat exchangers. So if you go into the conduction questions, in the year 2020 there is one question on plane walls. Then in 2019 you have a bundle of questions. That's what as really looking at it. You have composite wall question, you have overall heat transfer coefficient, you have question on thermal resistance, then thermal conductivity theory, then again a question on thermal conductivity numericals. Whereas in 2018, if you look at here, in 2018 there was a question on critical radius of insulation, there's a question on thermal conductivity theory, then again you have a question on transient lumped heat capacity analysis. 2017 you have a question on transient heat conduction, then thermal conductivity theory, then composite slab theory, then lumped analysis. 2016 there was a question on critical radius of insulation, thermal conductivity numericals, and heat flow sizing problem theory question. So if we try to go and check at the question, the first question, if you try to take it out, the external surface of a wall of 3 meters height, he has given a wall, 1 second, I'll just, I'll take the pen, yeah, I'll try to take a pen. See, there's an external surface of a wall, he has given a wall, this is a wall, wherein he has given the dimensions, different dimensions were being given. Its height is 3 meters, 3 meters is the height, and then 5 meters is the width, that's fine. And then he has given a thickness of 0.5 meters, this is 0.5 meters. Now we should always know that in one-dimensional heat conduction problem, heat always jumps from that particular dimension where thermal resistance is minimum. Thermal resistance depends upon the thickness. Say suppose if you look at it, it can be from here or it can be from, it can be in Y, it can be in Z, or it can be in X. So why I am trying to take along this particular boundary, Q dot is along this particular direction, this thickness is minimum where thermal resistance is minimum, so heat flow is it goes through this particular direction. So this is first one, and he is clearly saying that if the heat loss of 150 watts, so he has given this Q dot as 150, and then he has given the temperature. See, the external surface of the wall, 3 meters height, 5 meters width and 0.5 meters thick is at a temperature of 2 degrees centigrade. So this particular temperature is at 2 degrees centigrade. If the heat loss is 150 watts from the room across the wall, find the inner wall temperature. He is asking you what is the temperature of this. Say suppose if I call it as T1, thermal conductivity of material is given as 1 watt per meter Kelvin. So your relation goes simple, Q dot is equal to Ka delta T divided by L. So if I am writing this in terms of a numerical, say I'll take 150 is equal to K is 1, area is 5 into 3, this is 15 meters square, so 15 into T1 minus 2 divided by thickness is 0.5. So this is 75 divided by 15 is 5. So T1 is around this comes out to be around 7 degrees centigrade, which comes out to be 273 plus 7 comes out to 280 Kelvin. So your answer is 280 Kelvin. I will roll to the next question. That means this particular question is given on the very simple concept, the very first one, very simple concept based on your Fourier law applicable for steady state. Why I took steady state is neither time is asked. When I'm switching it, I have to take neither time is defined, nor thermal diffusivity is defined. So I assume this parameters are not given. So I'll try to take this as a steady state problem and then solve it. That's the solution. They are simple, but only thing is the situations, we have to look at the situations and then we have to arrive at the solutions. Now I'll try to go to the next particular question. The question is like this: the rate of heat flow through a composite wall of 3 layers of thickness. Now here he is giving you a composite slab and specifying that their thicknesses are given. Say suppose if this is K1, this is K2, and if this is K3, he has given 3 layers of thickness, 0.3 meters and then 0.2 meters, and this is 0.15 meters, not to scale. And corresponding thermal conductivities, he has given this value as 1.2, this value as 0.8, and this value as 0.6 kilojoule per hour. You can convert that into watt per meter square Kelvin or watt per meter square degree centigrade, but I don't suggest that you go, because all units of heat is also given in terms of your kilojoule per hour. So if the surface, and he is telling clearly that the amount of heat that is being flowing through this value Q dot is around 1280 kilojoule per hour. If the surface area normal to the direction of heat flow is 1 square meter, he is saying that, say suppose you try to take this as a composite slab, the heat flow area, this area which is uniform, I am assuming that the composite slab is prismatic, it is not tapered, its dimensions, area remains constant. So area is taken as 1 meter square and inner surface temperature is 1000 degrees centigrade. That means specifying that this particular temperature is 1000 degrees centigrade. Then interface temperature at the end of first layer, he is asking you what is the junction temperature here, that's all, Tj1. So it is a simple circuit. This is 1000 degrees centigrade, this value is 1000, and this is Tj1, junction temperature at the first interface, because it has 2 junction temperatures. So I am not taking the remaining 2 resistors, and the amount of heat flow I know, and this resistance is thermal resistance 1, which is equal to L1 by K1 A. So if I am writing it, Q dot is equal to delta T divided by thermal resistance. If I get that value of thermal resistance L by Ka, L value is 0.3, L1 or this particular thickness, divided by its thermal conductivity 1.2 into area is 1. So this becomes 1 by 4. So I will write this particular relation in a clear way, that 1280 is equal to delta T 1000 minus Tj1 divided by this value , So I can calculate Tj1 is 1280 by 1/4 comes out to be 320. So 1000 minus 320. This value should come out to 680 degrees centigrade. So your answer should be B. You need not write 3 circuits and then calculate everything. No, need not. Because as they are connected in series, same amount of heat is being flowing through them. So this is 1000 minus Tj1 divided by this particular resistance will give you the value. What I am observing it in this is, we are fighting with time. See, when a question paper is given, a good set of questions are given and it is time limited, even we calculate whether the student or the evaluator, whomsoever is doing it, can do it within that particular amount of time. So that's why, there is good amount of comprehensive passage where student tries to understand everything, but the question that has been asked is slightly, more corrective way. I appreciate the way these people generally, set questions. And if you look at the next question, this was questioned in 2019. In a furnace, the wall thickness is 60 centimeters and is 100 centimeters wide by 150 centimeters height. So actually, as he has not specified geometry, but as they are giving the dimensions, I assume that it is a plane wall. If it would have been any cylindrical geometry, they would have specified. So the wall thickness is 60 centimeters. So this is 0.6. And then its width is 100 centimeters. So this is 1 meter width. And its height is 150 centimeters, which is coming out to 1.5 meters. So I am getting an area of 1.5 meters square and the heat is flowing across this particular boundary, one dimension. Thermal conductivity is given 0.4 watt per meter Kelvin. The temperature inside and outside are 1000 degrees centigrade and 4 degrees centigrade. So see, if you are really observing it, the questions that were being framed are basically applicable to the applications pertaining to space. So he is saying that this is around 1000 degrees centigrade high temperature and this temperature is coming out to around 4 degrees centigrade. The thermal resistance is asking you what is the thermal resistance. Thermal resistance is equal to L by Ka, simple. And if you are taking it, its thickness is 0.6. Thermal conductivity is given, material 0.4 into its area is given as 1.5. 15 fours is 60. So this comes out to be 0.6 by 0.6, 1 watt per meter Kelvin. So if you observe it, they are trying to see to it, you read the comprehensive passage, but finally they are asking you a simple thing like thermal resistance. That's good. So the extrapolation of this particular concept is they can ask resistance pertaining to spheres. For cylinders there is a logarithmic term. So I suggest that there is a possibility of asking either the concepts on your thermal resistance of spheres or geometric mean areas, or they may give critical thickness, geometric mean area, ask the thermal resistance of a sphere. So for spheres, please try to understand, if you can convert it back into a plane wall, the thickness corresponds to radial thickness of the sphere and area corresponds to GMA, geometric mean area, 4 pi R1 R2 under root. Thereby again its thermal resistance is given by radial thickness divided by GMA into K. That again comes back to 1 by R1 minus 1 by R2 divided by 4 pi K becomes the thermal resistance. So see, whenever they try to give a question, they'll try to move around the same concept. They don't deviate, and then you have to get it within no time. Time is another parameter. Then yeah, these questions were really thought provoking. There were two particular questions they have been asking on theory part. The highest value of thermal conductivity is expected for, see, whenever you talk about variable thermal conductivities are highest, if you are observing the theory, they are for non-metallic crystal structures. Non-metallic crystal structures. Non-metallic crystal structures have highest thermal conductivity. In that, comes diamond. Diamond has a thermal conductivity value of around 2300 watt per meter Kelvin. So, if you observe it, it is not a non-metallic crystal structure. Then that means thermal conductivity of gases is less than thermal conductivity of liquids, is less than thermal conductivity of solids, because conduction is observed in all three states of matter, because it is because of molecular collision. Molecular dynamics deal at the surface. Intermolecular energy interactions are your conduction. So conduction is observed in all three states of matter. It is more dominant in solids, less in liquids, least in gases, because the molecular activity as you move from liquids to gases, it deteriorates. Rather than calling it as deterioration, I can clearly say that molecular interactions exist, but it is not as dominant as that in solids. So in this, if you observe clearly, whether it is steam is a binary phase vapor, and then you have water, it's a liquid. Superheated steam, yes, that is, they carry more amount of heat, enthalpy, but not thermal conductivity. So highest thermal conductivity is observed for ice, solid, as long as it is not melting. So answer is ice. Then say suppose I give different, I have that particular question. If I am looking at it, I'll come back to that question, that part of it, when I discuss about this. So you have one more question in 2019, 3 metal walls of same cross section area of cross section is same, area is same, having thermal conductivities in the ratio of 1:2:4. So he is saying that K1 is to K2 is to K3 is 1:2:4, and transverse heat at a rate of 3000 kilojoule per hour. So Q dot is constant all throughout. So it's a series combination for the same wall thickness. That means he is saying that L1 is equal to L2 equal to L3, the temperature drop will be in the ratio. See, we should always know that Q dot is equal to minus Ka dou T by dou X. So here Q dot by A flux is equal to K into minus dou T by dou X. That means this product of thermal conductivity into temperature gradient, this always remains constant. Now let us try to transfer it to, because he said it is a wall, he is saying that it is a wall. I will transfer this to a wall so that I can write this value Q dot divided by A is constant for all, and this value is K1 into delta T1 divided by L. And this L is constant all throughout, is equal to K2 into delta T2 divided by L is equal to K3 into delta T3 divided by L. I will call this as some lambda. And as thickness is also same, I can say a thermal conductivity into product of temperature drop remains constant. So I can say that K into delta T is constant. Hence, I will write delta T1 is to delta T2 is to delta T3, because delta T1 I can write it as some lambda divided by K1. delta T2 is written as some lambda divided by K2, and similarly this value of K3 is written as delta T3 is written as lambda by K3. So this is, I can write it as lambda by K1 is to lambda by K2 is to lambda by K3, because thickness is also same. So now I will remove this particular lambda, I will cancel this particular lambda, and then come back and write delta T1 is to delta T2 is to delta T3 is equal to 1 by K1 is to 1 by K2 is to 1 by K3. And the best answer that suits, basically it is 4 is to 2 is to 1, but he has given it in the regular form. I can write it as 1 is to 1 by 2 is to 1 by 4. This is the answer. So this is a good question. This is based on one very good concept. That particular concept is this. So always questions can be asked on it. Whenever you are having a composite slab, the product of thermal conductivity into temperature gradient always remains constant. Suppose you have a high thermal conductivity material as one particular slab, gradient will be less. If you have low thermal conductivity material, your gradient will be more. Or in other words, if they have same thickness, if high thermal conductivity material, temperature drop will be less in that particular material. Say, if I say that out of these two, this is K1, K2, if their temperature profiles are something like this, with all the given conditions, and then this is on the surface, then you tell about K1 and K2 means K2 is insulator, K2 is less than K1. High thermal conductivity material, this drop in temperature, this is delta T1. This value of delta T1 is less than compared to delta T2. So product of thermal conductivity into temperature gradient remains constant. That's why whenever you have a constant heat flow across a composite slabs, you observe this particular variations. I will roll to the next question. Hope I'm not running out. Yeah, I have the overall heat transfer coefficient. See how beautifully the questions were being framed. If you look at the overall heat transfer coefficients, generally whenever you have a conductive convective environment, conductive convective environment, what I will do, I will try to write this in terms of a total convective environment that is being equivalent to a conductive convective system. So how do we write it means, we say that the total rate of heat flow is equal to U into AS into delta T, and this value of Q dot can be written as delta T divided by total thermal resistance, R total. So from this, if I equate these two, I will be getting U into AS, one second, okay, this don't take it, U into AS is equal to reciprocal of total thermal resistance, and I am saying clearly here that they have a composite wall of thickness x1, x2, x3, K1, K2, K3, areas are constant. So I can write, because no convective system is being specified here, I can write total thermal resistance is equal to L1 by K1. L1 is x1 by K1, A is same, or A plus x2 by K2 into A plus x3 by K3 into A. So I can write U into A is equal to total value of this. I will take A in the numerator, So I will write it as x1 by k1 plus x2 by k2 plus x3 by k3. Now check, I will cancel these two. U is equal to 1 by this total value, or this value is equal to 1 by u. The answer that suits, if you check it, 1 by u, no, this value is 1 by u is equal to x1 by k1 plus x2 by k2 plus x3 by k3. So the examiner is trying to check whether are we able to match up, are we able to meet that particular standards rather than matching whichever it is. So I generally don't indicate that students should look there and here, no, need not. Just look at it, complete your analysis, then go back and check which multiple choice question would suit for you. Then this is really a good question, because overall heat transfer coefficients can be asked even in heat exchangers. That possibility is there. So in a heat exchanger, if they give a heat transfer coefficient inside and heat transfer coefficient outside, then you can write overall heat transfer coefficient can be approximated to be U is equal to Hi into H naught divided by Hi plus H naught. And if any of you have written your IES examination this year, the main paper, there's a question on this. He has given internal heat transfer coefficient. He has given external heat transfer coefficient value. Internal he has given in terms of Reynolds and Prandtl number. Reynolds and Prandtl number. Thereby, you estimate and then use this. There's a possibility of asking a question. Then I will roll to a theoretical question. Critical radius of insulation for a spherical shell is, for cylinder k by h naught and for sphere 2k by h naught, and the answer is critical radius is 2k by h naught. And mind you, this is the point where maximum heat transfer occurs, beyond which heat transfer reduces. If outer radius is less than critical radius, and by addition of insulation heat transfer increases up to critical radius, beyond which it decreases. If outer radius is more than critical radius, and then by addition of insulation heat transfer always decrease. And how to check in the exam whether it is h naught by k or k by h naught? This k has a unit of watt per meter Kelvin. This has a unit of watt per meter square Kelvin. So finally you should get unit of meter. Dimensional analysis, units and dimensions are fundamentals for making any of the relations, to know the correctness of the relation. So your answer is 2 times thermal conductivity of insulating material to heat transfer coefficient at the outer surface. This is the answer, B. Then see, if you look at it, there are theoretical questions that are coming. This is a question in 2018, and if you are looking at 18, again there is one more question. Which of the following has maximum value of thermal conductivity? I always go with this particular concept of variable thermal conductivities and which material has high and which material has low. If you look at it here, he has given only solids. If you have given solids, you clearly note that thermal conductivity of non-metallic solids, amorphous we call it, is less than thermal conductivity of alloys, is less than thermal conductivity of pure metals, is less than thermal conductivity of crystal structures. Crystal structures at STRUCTURES, crystal structures at reference temperature of 288 Kelvin or 15 degrees centigrade. Now again you look at it, what happens with variable thermal conductivity and temperature is increased. If temperature is increased, for pure metals it decreases except aluminum and uranium, and in case of alloys thermal conductivity increases. This is at reference. Now, if you observe it, he has given only pure metal. He has given only metals, if you observe, and alloys. And the first point that we should understand is highest thermal conductivity is observed in pure metals. And again in pure metals, how to look at it is a good conductor of electricity is equivalently good conductor of heat. Lorentz law. So what we do is, we'll try to look at which has highest electrical conductivity and which has highest thermal conductivity. So one which has good electrical conductivity is an equivalently good conductor of heat, highest thermal conductivity. So copper has highest. And when you look at next the alloys of copper, it's brass, then aluminum, then you have steel. So in this, which of the following has maximum value of thermal conductivity? Means one which is good conductor of electricity is equivalently good conductor of heat. So first point is that. Second is pure metals have highest thermal conductivity than alloys. So in this, pure metals are copper and aluminum. Copper has a thermal conductivity of around 400, 401, 389 to 401 watt per meter Kelvin is thermal conductivity of copper. When you go for aluminum, 205 watt per meter Kelvin. Steel comes down. It comes down to around 20 watt per meter Kelvin. Alloy, when you are adding impurity, iron, when it is there's an impurity with carbon, it forms a structure of more strength, but its heat dissipation values are decreasing out. So steel is lowest and brass is also an alloy. So answer is copper. Highest thermal conductivity is observed for copper, and its value is, thermal conductivity of copper is approximately around 400 watt per meter Kelvin. See, you have to read the initial first five pages on thermal conductivity is must tackle such questions. Yeah, this is one very interesting question where he has given accumulations. See, till now we were not talking about accumulations. See, just read the question. This is a very good question. The distribution of temperature at a particular instant. Whenever he is talking about instant, it is talking about transient nature. So you are talking about variation of temperature with respect to time. Across a large concrete wall 1 meter thick, which is heated from one side, is given by an equation. He has given a variation of temperature. So temperature is varying as 150 minus 80x plus 16x square. It's correct. Where distance x is in meters and t is in degrees centigrade. Fine. Thermal conductivity of wall. He has given thermal conductivity of wall as 0.6 watt per meter Kelvin. Area of cross section A is given 10 meter square meter. The heat accumulated unit time at this instant in the concrete wall. You see, in steady state there is no accumulation. If you observe any steady state phenomena, say suppose if Q dot 1 is entering and same Q dot 1 is leaving, then Q dot accumulation is 0. This is your steady state. That's why there is no rate of rise in internal energy. Right hand term is equated to 0. But if you come back and look at transient nature, some amount of heat is coming in Q dot 1 and some amount of leaving Q dot 2. He is asking you what is Q dot 1 minus Q dot 2. Fourier law is not just applicable only for steady state. Fourier law is an empirical law defined for one-dimensional heat flow, basically for isothermal surfaces, and it is applicable for homogeneous and isotropic materials. Wherever there is gradient, I can apply Fourier law, and hence I will write this value of Q dot 1 as minus Ka dou T by dou X at X equal to 0. And this value of Q dot 2 is written as minus Ka dou T by dou X at X is equal to 1 meter. That's all. And if I take difference, I'll get the answer. So I'll just do this numerical for you. K value is given as 0.6, A is 10. I'll take the white ink. This is 0.6 and this is given as 10. So the product of K into A is 6. Now I will take the differential of this. If I take dou T by dou X is minus 80 plus 32x. I want dou T by dou X at X equal to 0, it comes out to be minus 80. The gradient at that particular instant corresponding to location X equal to 0. So suppose dou T by dou X at X equal to 1 meter, this value is minus 80 plus 32, 50 minus another 2, so minus 48. And its units, regular unit, Kelvin per meter, or degree centigrade per meter, because differential temperature expressed in Kelvin or centigrade is same. So that should not be a hindrance for you to again say why I am not converting centigrade into Kelvin and all, right? Now this value comes out to, this value implies Q dot 1 is minus 6 into minus 80, comes out to be 480 watts. Q dot 2 is minus 6 because K into A is same, into minus 32. So 6 2s are 12, 163 is 18, plus 119, 192 watts. 480 minus 192. Q dot 1 minus Q dot 2 is Q dot accumulation. This is Q dot accumulation. This value is equal to 480 minus, this is 6 into 2, 12, and this is just a minute, yeah, this is not 32, this is 48. So this value is not 192, this value is 240 plus another 48, 288. So this value should be 288. Don't mind, check, I am trying to correct myself in this particular calculation. So this comes out to be around, this is 12 plus another 180. 12 plus 180 comes out to be 192. This is the answer. 192. What I did, in fact, I should not have this value. I took it as 32. That's why I was getting 192, but it is not 32, it is 48, which I got it here. Minus Ka dou T by dou X at X is equal to 1 meter. Then which of the following is false? Heat flow by conduction is directly proportional to area and temperature gradient. Correct. Because Q dot is equal to minus Ka dou T by dou X. Heat flow by convection is directly proportional to area and temperature difference. Correct. Newton's law of cooling. HAS into TW minus T infinity. Heat flow by radiation is directly proportional to cube. Wrong. No cube. Fourth power. This is wrong. Because your Stephens-Boltzmann law says for a black body, your emissive power or Q dot is equal to sigma AT power 4. It is fourth. Emissivity of perfect black body is unity. Correct, absolutely. A, B and D are correct. C is wrong. So C is the false statement, since Q dot is equal to sigma As temperature rise to the 4th power. Arrange the metals aluminum, copper, iron and silver in increasing order of thermal conductivity. Highest thermal conductivity is observed in silver, 439 watt per meter Kelvin. Suppose if I have given diamond, graphene, then they come up. They are non-metallic crystal structures. So here lowest corresponds to iron, yes, then comes aluminum, then comes copper, then comes silver. Answer is A. Answer is A. This is 439. This is around 400. This is around 205. This value is around 32, 40. Then, yeah, this is one very interesting question. An electric heater is sandwiched between two plates. He is saying that there are two plates, in between they have sandwiched a heater. As its dimensions are not given, I assume that it is negligible. This is 0.3, this is also 0.3. At steady state, that's good, because in a steady state there is no accumulations. At steady state condition, the heater is maintained at a temperature of 100. So you observe that the temperature here is 100 degrees centigrade and heat flow occurs both the directions. With a current of 0.25 amps. So he is giving current rating 0.25 amps. Voltage is being applied of 200 volts. So your Q dot is equal to V into I, which comes out to be 200 into half. This comes out to be 200 into 1/4, comes out to be 50 watts. Assume plates are perfectly insulated at edges and heater is having perfect contact with plate to give a temperature of 50 degrees centigrade. So he's saying that this particular temperature is 50. So use this particular relation, Q dot is equal to Ka delta T divided by L. And they should fetch you the answer. So they're trying to target the questions on the basic formulas, because I have lot more questions to go. So you can solve using this. Then for heat transfer across a composite slab with materials having different thermal conductivities, study the following statements. Temperature is continuous always, right? Because if temperature is continuous, then only gradients exist. If temperature is discontinuous, gradients doesn't exist, and heat transfer does not occur, because minus Ka dou T by dou X, it should be a continuous functions. So first one is correct. Temperature gradient is not continuous. Yes. Reason is if I am trying to take a composite slab, I observe that there is a variability in the gradient. The same gradient does not go in, because K into gradient always should remain constant. Heat flow is not continuous. Third is wrong, absolute wrong. So answer is statement 1 alone is correct. Statement 1 and 2 are correct. I go with statement B. Theory questions are always debatable. In fact, they are scientifically debatable to arrive at the solutions. Critical thickness of insulation yields no heat transfer rate from the pipe, wrong. Minimum heat transfer rate from a pipe, wrong. Maximum heat transfer rate from a pipe, correct. Corresponding to critical radius of insulation, heat transfer is maximum. If you try to plot Q dot on outer radius, we are observing that this point corresponds to critical radius, where heat transfer is maximum or thermal resistance is minimum. So answer is C. It is required to insulate a kitchen oven with a corkboard, so heat loss from the oven does not exceed 400 watt per meter square. When the inner surface of the oven is 225 and the outer surface of the oven is 40 degrees centigrade, thickness of insulation required is. You should solve this problem again with the same thing. Q dot is equal to K A delta T divided by L. And he has given clearly that heat loss should not exceed more than 400 watt per meter square. So area is 1 meter square. If you take it, this value Q dot comes out to be 400 watts. This temperature is 225 minus 40 is this temperature drop, and this particular value of K is given as 0.043, and is asking you what is the value of this particular thickness. So just check it. Your answer should be around 1 centimeter or odd. So you can directly calculate from this. Your thickness value L is equal to 0.043 into 1 into 225 minus 40 divided by 400. You will get the value in meters, and try to write this in centimeters by multiplying 100 or into 100, so it is by 4th, you will get the value. Then these two ends of rods of length L and radius R are made of same material, are kept at same temperature difference. Which of the following rods conduct most heat per unit time? See, if you are trying to tackle this particular question, is saying that there's a rod and this rod has a length equal to L and radius equal to R. Q dot is equal to Ka delta T divided by L for solid cylinders along axial direction. If I am trying to write, I'll write this as Q dot is equal to K, A is pi r square into delta T divided by L. So clearly materials are same, only thing is it is a sizing problem. That is what I was trying to say. K, pi, delta T, these three are constant. If I write it, rate of heat flow is proportional to R square by L. So if it's, what is he asking? Which of the following rods most heat per unit time? So it should conduct maximum. When is it maximum? Your thickness, your length should be less and your radius should be more. So check appropriately. Check appropriately. In these, this length is 50 centimeters. This length is 0.5 centimeters. This length is, this is 2 centimeters. This length is 100 centimeters, and the value of this is 3 centimeters. So whenever you are trying to write this rate of heat flows, check for maximum radius. So it should be 2 centimeters. Calculate, you will get the answer. So the metric is, it is proportional to R square divided by L. Then transmission of heat by molecular collision is conduction. Conduction. This is by conduction. The value of Biot number is very small when lumped heat capacity analysis, conductive thermal resistance is far less than convective resistance. So this is a concept of negligible internal resistance. So conductive resistance of fluid is negligible, wrong. Conductive resistance within the body is negligible, correct. This is correct. External resistance is negligible. No, that is semi-infinite solids. Answer is B. Then this is a packed bed problem. See what he said, there is a packed bed, it contains two spheres, one is made of copper, other one is made of aluminum, and is asking you which particular graph indicates the heating or cooling characteristics of aluminum or copper, and he has given that graphs. I think I have not included. See, whenever you are trying to write the same temperatures, T minus T infinity by T naught minus T infinity is e to the power of minus tau by tau star. If you observe it, time is same, but it depends on the tau star value. Tau star is given by rho v Cp divided by h into As. For spheres, rho Cp into volume divided by surface area is characteristic length. Volume divided by surface area is R by 3. So I can write R by 3H. This is your tau star value. Check tau star value first. So if I am writing tau star value for copper as well as for aluminum, so if I write tau star for copper, tau star for aluminum, this means its density, specific heat, radius divided by 3H, because he has given the properties. And here also I will write density, specific heat R divided by 3H, and whichever has higher will take the steeper curve. That means if I am trying to draw that particular graph, say initially it is at some temperature T naught, it has to reach that ambient temperature of the furnace. So if I am trying to draw, it is an asymptotic curve, it tries to reach, so they will reach like this. This corresponds to aluminum. This is aluminum and this is copper. So whichever value you will have it, that will be your steeper curve. And you are observing that this value tau star of aluminum is higher than the tau star of copper. Thermal time constants. Excellent question, can be repeated again and again. Very, very beautiful and important question. Excellent concept has been thrown up into it. Then yeah, this is I has given a question, whether is it convection question? Okay, I think it is, yeah, it is a convection question. It has come up into it. See what it says is a beaker is filled with hot water in a room, cools from 70 to 65 in T1 minutes, then 65 to 60 in T2 minutes, and 60 to 55 in T3 minutes. Then which of the following? See, as initial temperature, this is the case of cooling. This is the case of cooling. Say suppose you go with lumped analysis. It's a solid one. He has not talked about fluid. So filled with water. So I can write that this T minus T infinity divided by T naught minus T infinity is e to the power of minus tau by tau star. So I can write this is initial, say T naught 1. So it reaches T1, then it reaches T2, then it reaches T3 within a time frame of tau 1, tau 2, tau 3. So clear that suppose if it is linear, if this function would have been linear, then all three would have been same. But T1 is always less than T2 than T3, though temperature drop is same in all three cases. So answer for this is C. In convection, he has given natural convection. One elastic flow question was being given that comes into a different concept: Prandtl theory, mass transfer. Then again heat flow, boundary layers, Prandtl number, forced convection. Most excellent questions were being given only from Prandtl mixing line theories. And if you observe it, a fluid having a density of 1 gram per cc is in a state with Grashof number 2 into 10 power 6 and Prandtl number 0.7. Assuming acceleration due to gravity as 10 meter per second square, calculate Rayleigh number. And we should know that whenever there are gravitational effects, it is natural convection. Rayleigh number is product of Grashof number into Prandtl number. So this value should be 2 into 10 power 6 into 0.7. It should come out to 1.4 into 10 power 6. Then, which of the following statement is true for Rayleigh flow at Mach equal to 1? This is nothing to do with the syllabus of heat transfer, but there is compressible fluid flows. In compressible fluid flows, we talk about flow in constant area ducts without friction and with heat transfer. That is Rayleigh flow. So suppose if you are looking in constant area duct with friction and without heat transfer, Fano flow. So as there is a word of heat transfer, I believe they should have given this, because these flows occur outside boundary layers. So they are elastic flows where the state is given by Mach numbers. It is given by Mach. So whenever you come for compressible fluid flows, we have enthalpy entropy diagram, and then you have a Rayleigh curve. This is Rayleigh, and basically you have a Fano curve like this. You have a Fano flow. So one flow is Fano and other one is Rayleigh, R-A-Y-L-E-I-G-H, Rayleigh flow. So between them your shock flow occurs, and it always occurs, this intersection always occurs in the direction of increasing entropy. So you can refer to a very good book like compressible fluid flows by Shapiro, or compressible fluid flows by E. Radhakrishnan, or S.M. Yahya. These particular concepts are given. Rayleigh flow is that flow in constant area duct without friction and with heat transfer. So this is the particular point of Mach equal to 1. You will not have a flow from subsonic to supersonic. You will have subsonic to sonic or supersonic to sonic. So at this particular point, entropy is maximum. This is point of maximum entropy and minimum enthalpies. So I should redraw it. So answer is entropy is maximum and enthalpy is minimum. So answer is both B and C. I'll just roll back with another 5 more minutes. Analogy between momentum and heat transfer is given by, analogy between heat transfer and momentum is given by Reynolds-Kalban analogy, generally we call. So Chiton-Kalban analogy talks about even mass transfers also. But if you write your Reynolds-Kalban analogies, Stanton number into Prandtl power 2 by 3 is equal to Cf by 2. So it is Stanton number is there, Prandtl number is there. I can call it a Stanton-Prandtl analogies. Suppose if it is for Prandtl number equal to 1, it is called Reynolds analogy. Or sometimes this is also called as Reynolds-Kalban analogies. But it is good to go ahead with Stanton-Prandtl analogy. This Chilton-Kalban analogy will give you a wrong misnomer between your Reynolds-Kalban analogy, because Kalban is in both, but Chilton-Kalban analogy is a holistic double diffusion process wherein you even talk in terms of mass transports along with heat transports. We are not considering it. The typical range of Prandtl number for water is, for water at room temperature, its Prandtl number is around 13.7, and corresponding to around 100 degrees centigrade it is around 1.7. So answer should be 1.7 and 13.7. So this is ratio of convective mass transfer to mass diffusion rate is called Sherwood number. This is from mass transfers. This problem is to be solved with a simple concept of Q dot is equal to H into AS into TW minus T infinity. Straight question. Because Q dot is given, surface area is given, H is given, he is asking you the wall temperature of the heater. Answer comes out to be around 60.5. And this is always a question that is asked, hydrodynamic boundary layer thickness to thermal boundary layer thickness. This is Prandtl to the power of 1 by 3, or in our books it is given as thermal boundary layer thickness to hydrodynamic boundary layer thickness is Prandtl to the power of minus 1 by 3. This is called Prandtl's 1/3 law. When Prandtl number is equal to 1, both of them are same. So delta H is equal to delta T. Not to discuss, but no, I am also transient nowadays. I can't be steady. I can't say that I am independent of time. So whatever questions I have been discussing it, these particular questions are very important, and please try to look back at them, and let's have some more sessions next time. Thank you. Catch you. Bye. All the best.